dimensions is like an object is moving along the x-axis and along the y-axis at the same time. Remember in the last chapter we were talking about objects falling. That was only motion along the y-axis, isn't it? Or maybe we were talking about driving a car on a flat road, which was motion only along the x-axis. See that? So that's why it was one-dimensional motion, and now it's going to be motion along two dimensions, like, will it break? No, like that. Didn't it move forward? Didn't it also go up and then down? That's an example for two-dimensional motion. Because it was moving along the x-axis, it was also moving along the y-axis. And in our heads, right from the start, we need to remember that these two are completely independent of each other. Motion along the x and motion along the y do not affect each other. I know it's just one object, right? But you have to have this. What am I saying? The acceleration due to gravity acts only on which axis? The y-axis. So when you throw an object up, its acceleration is only along the y-axis. It has no acceleration along the x-axis. Are you with me? So in this chapter, we're going to have to say, we have to add a subscript x and y. So when we say initial velocity v naught, that's not enough. We got to say v naught x, v naught y. Now for acceleration, we got to say ax and a sub y. You get what I'm saying? But fortunately for time, time is a scalar. Time is just time. Like how much time did it take to go from here to that point? We can't talk about what's the time along the x? What's the time along the y? No, it just took a certain time. Getting what I'm saying? So velocity and acceleration are vectors. We need to have the x and the y components, but time, there's no need. What about displacement? Is it a scalar or vector? Displacement. Vector. So again, you will have delta x and you will have delta y. Already you can see how that's... We're going to use the same equations. Like in the last chapter, just remember that you have to treat them individually. So we start with a simple example of this person who is walking 9 blocks to the east. 9 blocks to the east, and then goes, how many? 5 blocks north. So what's the displacement along the x-axis? 9 blocks east. What's the displacement along the y-axis? 5 blocks north. But what is his actual displacement? You know, remember, displacement is the shortest distance between the starting point and the finishing point. So this person actually started from A and finished at B. So his actual or her actual displacement is just the vector AB. So that's what I've written here. What is the displacement?
Is it 10?
We got to find that in a minute. So, but did you understand that the actual displacement is AB? Hold on. What is the distance that this person moved? What is the distance that the person moved? 9 plus 5, 14. Can you give the direction? No, it's just 9 and 5. So the distance was 14, but the displacement is not 14. The displacement is AB, right? How do you find that? Do you see a right angle triangle there? And how do you find that? Everybody knows, square both sides, yeah? Square both sides and add them, take the square root, you get that. Is that making sense?
Would it work if we did the opposite of what Jason and?
Let's actually do the reverse of this. Let's imagine that the displacement AB is given, right? Would you be able to find its x component and its y component? we're doing this in reverse. So we've just given the displacement is 10.3 units and the angle is given. This angle is given, okay? I'm going to show you how to break that into two. There you go. AX is 9 units. AY is 5 units. Did that make sense? Hey, isn't AX 9 units? What's AY? 5. So you can work both ways. So if you're given this, you can actually break it up with 9 and 5. And I'm going to show you how in a minute, but this theta, this angle theta, how many people know how tan is defined? Tan theta. Opposite over adjacent, which is the opposite side. If this is the angle, the opposite side is this one, which is 5, right? And the adjacent is 9. So tan theta would be opposite over adjacent, which is 5 over 9. Put in your calculator, find that. 29 degrees with the x-axis. And here I thought I should teach you this. I'm sure you know, but if you don't, sine is, come on, opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So I'm just writing that. And you may not get time to write all this, but that's why it's going to be on the video there. Sine theta is 3 by 5. Cos is 4 by 5. Tan is 3 by 4. And again, you have to use this. Now, what's this theorem called? Everybody knows that, right? If you square this, it's the sum of the squares of these two. So if you have this, you're good. 30 meters is the displacement. 25 degrees is the angle. Please find AB and BC, which is AX and AY. See, I'm just calling it AX and AY. Find the components of this. And an easy way to remember it will be this. Look, the horizontal is always cosine. The vertical is always sine. If you take the angle with this, okay? So what am I saying? This will be, help me out, please. 30 times, yeah, AX. AX will be 30 times cosine 25. And AY will be 30 times sine 25. Is that clear? Should I try again? One more time, sure. The x component will always be whatever the vector is, which is 30, cosine of the angle. So 30 times cosine 25. And the y component will always be 30 times sine 25. You see the difference? One is cosine, the other is sine. So get that for me, please. And I'm actually detailing how you get it. So you just get that. And you should be able to get 27.2 meters and 12.7 meters. I told you, and I'm stressing it again, the horizontal and vertical components of two-dimensional motion are, what's the most important word there? Independent of each other. Any motion in the horizontal direction does not affect motion in the vertical direction and vice versa. See that? That's so tough for students to do in their head. It's like, no, isn't it the same object? You have to remember that. It's independent. What affects the vertical does not affect the horizontal. So let's move on. Here is a real nice question, bringing it to the practical side. So there is a red ball and a blue ball at the same height. The red one is simply dropped, goes straight down. That's one-dimensional motion, isn't it? But the blue one is actually given a velocity in the horizontal direction. So that means the blue one is not dropped, but it is thrown, something like this. The blue one is like given, I'm not giving it at an angle, you can see that. It's thrown horizontally, right? But from the same height. Which one hits the ground first? Did you think? All right, did you, wait, I don't know who said the answer, but you did not think. So, which one hits the ground first? The red ball or the blue ball? Which one? Are they dropped from the same height?
Yes.
All right, we're going to find the answer together. Are they dropped from the same height?
Yes.
Is the delta y the same for both? I'm only talking about delta y. See, this is where in your head I am talking about how much did they go down. Is that the same for both?
Yes.
Good. Is the acceleration due to gravity same for both? Yes. Did they both start with the same initial vertical velocity?
Yes.
What was the initial vertical velocity of the one that was dropped? It was 0. What was the initial vertical velocity of the one that I had projected horizontally? I'm trying. Can you see that? I gave it a horizontal velocity. I did. But its vertical initial velocity was still how much?
0.
So all the quantities are the same. Along the y, let's go back again. Along the y, the initial velocity for both was 0. They both have the same acceleration. They both have the same delta y, so they need to have the same time. How many understood? Thank you. Both will hit the ground at the same time. Any questions? What am I doing there? What am I doing? Just take some time on this. What is the velocity that I gave the blue one? Do you see why it's Vox? Do you really? Okay, here we have the y for the red one. I'm assuming it takes 3 seconds. Okay, that's what I threw in there. 3 seconds to hit the ground. Find delta y. Isn't this the equation we would use? Come on. So what was delta y? What was delta y? Negative 44.1 meter. For which ball? The red ball. Now let's go to the blue one. Is it also going to take 3 seconds to hit the ground? That's what I was shouting about. So will delta y be the same for that? Yes, delta y is the same for both. But the blue one also moves along the x-axis, doesn't it? We're trying to find that. See what I used. Why did I use this equation? What do you know about this velocity? Is it affected by gravity? Wait a minute. Is this along the x-axis or the y-axis? Does gravity affect anything along the x-axis? So what do we know? We know that this velocity is a constant. It never changes. See, if it never changes, then the equation we use is this. Multiply that velocity with the time. This is going to fall 30 meters away. All right? Let's check whether you understood. You work out this problem all on your own. Only difference is, imagine that the time is 4 seconds. Imagine that the time is 4 seconds. Find delta y and delta x for the blue ball. Find delta y and delta x for the blue ball, assuming that the time is 4 seconds. That brings up a good question. What is the delta x for the red one? What is the delta x for the red one? Shout it.
0.
Yeah, it falls right there, right? So delta x for the red one is 0, of course. And I think you got the answers by now, did you? If it's 4 seconds, delta y should be negative 78.4 meter. How many got that? 78.4, negative 78.4. And delta x is going to be, of course, 10 times 4, 40 meters. How many got that? Good. So some of you Need to catch up, so ask me a question if you have one. Writing, because this is just summarizing. What did we talk about? We talked about if there is a vector, you can resolve it, break it into ax and ay, and find the angle. Isn't that what we talked about? Okay. We did that. We saw that the x is always a cosine theta and the y is a sine theta. Right? And you can find the angle using tan inverse ay by so that's all stuff that we talked about. Here is another thing. Addition of vectors. Addition of two vectors. Watch this carefully. First try to understand. There is a red vector, which is A, and there is a blue one, B. Here's a problem. Let's assume it's somebody walked from here till here, a certain distance, and then they walked from there to there. Isn't displacement this? Come on. Right? So how do you find the displacement in this case? Because this is not like the 9 blocks and the 5 blocks, because that was easy. Why? Because that was a right triangle, but now we don't have a right triangle, so we're going to have to get a right triangle. Sorry, guys. So to get the right triangle, this is what we do. The same thing we've been talking about. Watch this. Do you see in this diagram that this vector has an x? See that? And has a y? Come on. Yeah. So if I had given you this angle, you would be able to find this and this, correct? And then, now look at the blue one. Wouldn't that also have an x and a y? And if I had given you that angle, you would be able to find those. Agreed? Good. We're almost done. So now what you do is you add the x of the first one, which is ax, with the x of the second one, which is bx. Do you see it here? I've added the x of A and the x of B. Come on. Do the same with the y. Isn't this the y of A? Isn't this the y of B? So I've added the y's. Now, do I have a right angle triangle? Do I have a right angle triangle? Are you following me? Now what can you do? You just square this, and add them, take the square root, right? That's it. That's how you find two vectors. Like 5 questions on this part on the exam, because this is like real thing. You remember when I threw that pen or the marker? That was a projectile. In athletics, when you throw the shot or throw the javelin, that's a projectile. Doesn't it have an initial velocity? Watch. Well, I hope you won't give me a wrong answer. When I project it, which I'm not going to do, what's the initial velocity?
0.
Oh! The initial velocity is not when I have it in my hand. The initial velocity is what I give it when I just release it. Is that making sense? Therefore, the initial velocity is never 0 for a projectile unless it's dropped. Then it's 0, you see? So, get that correct first. The initial velocity is not 0. That's not when I'm holding. It's when I let go. Didn't I give it some velocity? Okay, so a projectile always has a certain velocity. And I called it V0. Let V0 be the initial velocity. You see that vector? Do you see that vector V0? And isn't that at a certain angle? Yeah, with the horizontal, didn't I throw it at a certain angle? So the first thing you do is you break it into its 2 components. What do we call this? Is this V0x or V0y? All right, this is V0y. So if this is theta, can you please label what this is and what this is? Can you label? That angle is theta. That angle is theta. What is this? I've been talking about that like for the last... No, I told you the horizontal is going to be always cosine. So that means this will be V0 cosine theta. This would be V0 sine theta. That's what I'm trying to say. V0 cosine theta And let's assume V naught is 20. So that'll make it more sensible. Okay. So can you now plug in those numbers and find the x and the y components? I know that 20 sine 30 is going to be 10. Did you get the y component as 10 meter per second?
Yes.
And this one, wait, cosine 30. So it should be 17.32. Am I right?
Yes.
17.32. How many got that? Let's see. Both. Very good. Class moving on. The others catch up. Vertical. Y-axis is the vertical. V over y is V naught sine theta, which is, I'm only talking about the vertical now. 10 meter per second. Let me stop right there. We are only talking about the vertical. Isn't that the vertical component? V over y is V naught sine theta, which is 20 sine 30, which is 10. Okay. What else do we know about the vertical? Is there an acceleration along the vertical? Is it 9.8 or negative 9.8? Negative 9.8. Okay. So acceleration is negative 9.8. We know that. Hey, here's a nice question for you. Watch. It's starting from A. It's ending at B, isn't it? So it started from the ground, finished on the ground. How many of you can tell me what delta y is?
0.
Two people had the courage. Whether right or wrong, they had the courage. Okay. It started from here, from the ground, and ended back on the ground. How much did it go vertically? What is delta y? 0, of course. Okay, now you know what's going to happen to some students. Some students are going to be like, no, isn't A here and B here? Hey, that's delta x. See that? See that? What are we talking about now? We're talking about, look, if I did throw something from the ground, hello, watch this. If I throw something from the ground and it lands on this table, is delta y 0? Delta y is now plus something, the height of the table. Agreed? Okay, next case. If I throw something from the ground and it lands into a hole in the ground, is delta y 0?
No.
Delta y is negative something. Can I see the hands of those who understood? You're good. You're good. That's all. This chapter is fine. So you got to always think. You throw it from the ground. Does it land here? Delta y is positive, the height of the... Or I throw something from a table and it hits the ground. What's delta y? Negative, the height of the table. That's all. You got it? So in this case, delta y is how much? 0. Delta y is 0. Can you find the time? Can you find the time? Go. Do you know the equation to be used when you have these four quantities? We do. Do you know the equation? So you write that equation which is coming up, plus 1/2 AT squared. Plug in the numbers carefully. Just check what I used for V naught y. Did I use 20? Did I use 20? Huh? Did I use 20 or did I use 10? So 20 is gone. 20 is replaced with 10. You see? V over y is 10. That's another mistake students make. So it's 10. All right. And then do that. Divide both sides. And you get 2 seconds. Do you? Get 2.0 seconds. How many of you can find delta x? Go ahead. How far away? Now we're talking about the horizontal. How far away does it fall? We're trying to find this displacement. Delta x. So which velocity are we going to use? Are we going to use v over y or v over x? Definitely. Didn't we already get VOX? I thought we said 17.32 meter per second. Was it? So now you use that. I'll let you finish it. Don't we know that along the x-axis, the velocity never changes? Along the x-axis, the velocity never changes, right?
Right.
So there's only one equation we can use on the x-axis all the time. Who remembers that equation? If the velocity is constant, what do you do?
The velocity times time.
That's it. On the x-axis, it's easy. On the x-axis, just multiply VOX with the time. Can you do that? So on the horizontal, here it's coming up. On the horizontal, which is the x-axis, delta x is VOX multiplied by time. And that's V naught cosine theta, which we found, which is 20 cosine 30, which we already have a 17.32, don't we? So 17.32 times 2, it falls 34.64 meters away. Any questions? We got the time? I had this diagram just to make things clear. I'm still talking about the same thing. Take a look. Take a look at this. I know it's not very clear. What I want you to see is that the vertical component of the velocity changes. First, the vertical component decreases. Let me just try to draw it. So it starts with that. As it goes up, the vertical component of the velocity decreases. Are you able to see it now? No? Can you see what I'm drawing?
Yeah.
And at the highest point, the vertical velocity becomes right. And then as it continues falling, now the vertical velocity starts, somebody help me, starts increasing. And by the time it returns, it's so tough to draw with this. By the time it returns, it goes back to what it was before. Did you understand? Okay, if you understood, you'll answer this question. At the highest point, at this point, what is VOY? Thank you. Now let's talk about the horizontal. And you see it here in this picture. What do you see about the horizontal? Look at the vector. Is it changing? No, the horizontal component of the velocity never changes. So if I use another color for that, okay, let's go with this. So if I take the horizontal component at every point, it is the same. I hope you're getting, it's so tough to draw it, but you're getting the idea, are you?
Yes.
So here's the final question. At the highest point of the projectile, is the velocity zero? At the highest point of a projectile, is the velocity zero? No. Is the vertical velocity zero?
Yes.
You getting it? Why isn't the velocity zero at the highest point? Because although the vertical is zero, there is still the... Do you get it? So in the last question, can you tell me what the velocity of the projectile is at the highest point? In this question, who can tell me? What's the velocity of the projectile at the highest point? 3, 2. Very good.
Okay.
What's the velocity of a projectile at the highest point? It's VOX. Because what happened to VOY at that point? Zero. Are you getting what I'm saying? So that might be a conceptual question. Are you seeing it?
Yeah.
All right. Yeah, VOX is 20 cosine 30, which is 17.32. VOX. Do you see VOX? 20 cosine 30, which is 17.32. Okay? Is the equations that we used from the last chapter? Yes, the same equations. The only difference is we had, do you see that? What is that? VOY. 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 Just remember, that's for the vertical motion. For the vertical motion, same equations. For the horizontal, what's the only equation that will work for the horizontal? Help me out. What's the only equation that will work for the horizontal? Come on. Only one equation. What is that? Delta x is equal to VOX multiplied by. That's the only equation that works on the horizontal. So for the vertical, all these equations. For the horizontal, just one equation.